All right, everybody, welcome back. I hope you had an amazingly filling lunch, and not so filling that you're all going to fall asleep, because I'm going to try and wake you guys up and get you super interested in testable code in D. All right, so how many of you folks have actually written a unit test in D? I am super thrilled to see that a bunch of you have done that. Okay, so 90% of my job is done. You guys can all go home. My name is Ben Gertzfield. I'm an engineer here at Facebook. I work on testability and mobile software. And I want you to take away one thing and one thing only from this test. Tests can be easy to write as long as you separate out all the dependencies. And there's a lot of subtlety in this statement. And what I'm going to go through in this talk kind of explains why this is super important. Most of the unit tests you guys have probably written have been things for library code where you've got to make sure the input gives the expected output. You know, fairly simple stuff. A lot of the stuff in the D runtime is, all the math libraries and the standard, formatting libraries. These are kind of things that are typically really easy to unit test. How many folks here have tried to write a unit test for like complicated, server software or application software? It's a lot harder. And what's that? Failed completely, yes. So a really common scenario I see in testing is you spend a lot of time writing a bunch of tests for your software. Maybe they work for a week or so, and then they start failing due to changes elsewhere in the software. You're called in because you're the fellow who wrote the tests, and suddenly you're responsible for every change that anybody makes anywhere in the software. So there's a way out of this world, and that's what I'm going to teach you guys today. So first off, let's talk about why should we even think about writing testable code. As software engineers, all we do all day is make mistakes. And the worst thing in the world for an engineer is to make the same mistakes over and over and over again. So what you can do when you write testable code is you can start making new and interesting mistakes that you've never made before. And anybody who learns for their whole life, you're going to find that making mistakes is the only way that you learn. So let's all make new mistakes instead of old, boring ones. Another really important part is whenever you get to a code base of a certain size, it's terrifying to approach it. You might try to poke at some software you didn't write, and you find that something squirts out the other end. You had no idea that those two things were interconnected, and you slowly start following the threads through, and you see that all of this software depends on each other, and changing A makes Z spit out a different answer. Testable code makes sure that you don't live in fear of touching this code you didn't write. And the code that you did write about 6 months ago might be a little more approachable if you can actually reason about, hey, if I do change this, I can be confident that running the tests is going to catch any errors or regressions or changes in the contract to the outside world. Does this kind of make sense to everybody? Cool. So when you describe testing, there's some terminology that people throw around a lot. Do folks like, you've heard the word unit test, but you've heard terms like functional tests and end-to-end test and these regression tests and all these things. Is anybody actually comfortable with the difference between those? Because it took me a long time. All right, so let me talk a little bit about this terminology. So when you talk about a unit, it could mean a bunch of different things. This is not like an accepted definition. It could be a function, it could be a class, or in D, it could be a module, like a file. Like that could all be considered a unit. It's basically what can you wrap your head around? In terms of virtual memory, what can you page into your active brain and focus on before something gets swapped out because your brain is full and you can't think about it anymore? So that's basically what a unit is. And keeping that as small and focused as possible is a key to understanding and testing any bit of software. As soon as that unit starts growing past where your brain can wrap around it, not only can your brain not wrap around it, but the computer's going to have trouble testing it too. So keep your unit self-contained and small. So all of you have written unit tests sounded like in D, so this is not going to be very interesting to you, but let's give an example of unit testing in D. So D is, as far as I'm aware, and you can correct me if I'm wrong, I believe it's the first major language with unit testing built in. Is that correct? Yeah, so I don't know of any counterexamples either. There are a couple experimental languages. I've seen one coming out of Google that is focused around testability, but I haven't seen one that actually has major efforts in it before. But yeah, so the technical stuff is any code that's inside of a unit test block. Unit test blocks are at the top level scope, will be executed before main if you compile it with dmd-unit test. Every single unit test block in your program will run. So if you want to run just a single file, you might need to compile and run just that single file by itself. A unit test will generally contain some logic and some assert statements. You can use the same old assert statements you use in everyday code. So let's look what a basic unit test looks like. You've probably all seen this a million times before, standard implementation with bugs of Newton's approximation of square root. So we'll write a function to guess at the square root of a value, and we'll write a couple unit tests to make sure that the square root of 16 is roughly 4-ish. Square root of 0 isn't some sort of crash, and the square root of 10 is definitely, it's somewhere around, a square root of 100 is somewhere around 1. This is the easiest kind of unit test to write. If your job is writing unit tests like this, you have it easy, and my congratulations to you, because none of the rest of us get to write very many unit tests like this. So you might have heard the term integration test thrown around. So the way that integration tests differ is they're going to group together a bunch of different units and test all of them in concert. So a good example might be, let's say you're writing a server that needs to authenticate the user and talk to a database and log the user in and then maybe change some state for the user. That might be what's called an integration test. These things tend to be stateful, they tend to be a little more complicated, and they tend to break a lot more often. But they're important for making sure that all of your units are actually glued together. Because really, what do we do all day but glue together bits of other people's software? I mean, that's really what most of us do all day. But because they have such a large surface area, when you focus on one unit, you might have 5 tests to write. If you're focusing on 10 units, each of which have 5 different ways they interact with each other, you've got many, many dimensions, more things that can go wrong. So these types of tests fail a lot more often. Like, how many of you folks have worked on a unit test environment where some of the tests, they just fail once a week or so and nobody really knows why? Yeah. So what I'm going to teach you today is how to identify those situations and write software differently so that the tests themselves only fail when the code underneath, the code that they're testing is actually broken. Another term you might have heard is end-to-end test. So these are about exercising the entire process from start to finish, the actual lifetime of the process. You're only going to ever see or run into a couple of these. These are basically for smoke tests to make sure, oh my God, is the entire world busted? Can I actually start my app, do some basic operations and shut it down? You're only ever going to have 1 or 2 of these. And they get flaky, you can imagine, even quicker than integration tests. So don't spend a lot of time working on integration tests or end-to-end tests. What you want to focus on is making sure that the individual units of your software are well tested, like cogs in a machine. They need to be really well lubricated. The teeth need to fit really well together, and other metaphors that are totally inappropriate for software. So I want to talk about how to make a true unit test. So to make your code testable, the key is isolating the unit under test from its dependencies. And this is a lot more complicated than it sounds, because again, what is a dependency? Is malloc a dependency? It turns out, unless you really want to simulate the behavior of the dependent system, you can basically rule it out as a dependency. If you write a test where you really do want to see what happens when malloc fails, you might need to substitute it in a unit test environment. Basically, any component of your test that you need to have behave in more than one way, that's a unit that you want to separate out and make substitutable in your test. A term I'm going to teach you is something called constructor injection. Has anybody here heard the term constructor injection before? OK, this is going to be totally new for you guys, so this is great. Has anybody heard the term dependency injection? A couple hands. OK, so constructor injection is a specific technique of one of the ways to implement the tool called dependency injection, where you basically utilize the constructor of a class, and this is specifically for objects. You use the constructor of a class and the signature of it to indicate all of the dependencies of that class. These dependencies could be logic, so they could be code. They could be state, maybe caches or other sorts of state. Or they could be runtime parameters that aren't related to the code or data dependencies. So that's the constructor injection is basically a technique for if that list of dependencies changes, the signature of the constructor changes. And that means that any test that uses it breaks at compile time, which is really important. You want your tests to be linked to the code that they're testing in such a way that they fail as early as possible. If they fail at compilation time, the coder who's changed them knows right away, oh, maybe I should look at this test and see how my new piece of software impacts this test, and maybe I should write some new ones. So as an example, a lot of blank stares out there. So I'm going to give a concrete example of why this technique is useful. So this is kind of hard to read, isn't it? Let me see if I can zoom in a little bit. No, I cannot. OK. So this is a pretty flaky test here. So I'm importing standard socket. I'm going to use the mouse here. All right. So this is a test that, this is a piece of code that, given a host name, checks and sees if this has a DNS entry and throws an exception if there's no DNS entry. Maybe you're using this for some system reliability to check, oh, is my DNS working? And it has some systems to use the standard std.socket get host by name. And if it says there's no host, it logs something and throws an exception. And maybe I want to write some unit tests for it. So I'll say, OK, I'm going to call check host on dlang.org. Make sure it doesn't throw an exception. This is a really, if folks don't know about assert thrown and assert not thrown, these are really nice assert variants that make sure that the statement does or does not actually throw an exception. And I want to say that, OK, there's no Q language yet. We haven't made it to E or F yet. So hopefully we haven't made it to Q. And we're going to make sure that there's no Q language at org. So can anybody tell me, when is this test going to fail? Because ideally, I want it to fail when the code changes, right? What are some other times it might fail?
When the network's down, for example.
Yeah. It might fail when the network's down. That's a good one.
When somebody registers qlang.org.
If someone registers qlang.org, that's an excellent one. Yeah. I like that. Do you have any others? He's not a plant, by the way. He's my coworker, but I did not coach him. I did not coach him on that. Yes?
When the DNS server is down.
When the DNS, oh, that's not that one. OK, I didn't get that one. Yes. Yes, if DNS is down, that will totally cause this to fail. Another one that will cause this to fail is if the file system's full. And this is one of Andre's favorite, of course. If write or close fails, you've just failed this test. And guess what? People do run tests on read-only file systems. They do run tests on full file systems. Some of those flaky tests that you guys have seen, they're because the test implicitly or explicitly depends on the state of the network, the state of the file system, and maybe the state of the program. So again, identifying those dependencies and isolating them so that you can model them and change their behavior for the test environment, that's the key to making healthy and reliable tests that only fail when the code changes. Another time this test is going to fail is when I hit freaking Control-C, because this stupid test takes 30 seconds to run. How many of you have run tests that take like 5, 10 minutes to run? Like, everybody has. It's one of the worst experiences. Like, these tests are not terribly useful. They might be useful, like I said, for these types of smoke tests that are run automatically, once a day or something. But no engineer wants to sit there waiting for 10 minutes and test ready. No. Yeah, nobody wants to do that. So an example like this one, I tested this test. It actually takes 30.8 seconds to run. And that's because it has to time out many times waiting for DNS to fail. So let's talk about how we might make this testable. So we're going to use this technique I talked about, constructor injection, to write a new class that has a hope of actually being testable. What you'll see here is I've actually introduced some member variables. So I've got an internet host and a logger. So anybody who's looking closely at the top, I'm importing an std.log, which unfortunately doesn't yet exist. Are we close yet, Walter? OK, well, hopefully we'll have a standard logging system one of these. So let's go on the assumption that we have a standard logging system and it has a logger class. So all I've done is I've introduced a constructor that takes 2 parameters, an internet host and a logger, and it just stashes them away in member variables. And now the checkhost method is exactly the same, but instead of calling free functions, globals, or other things, it just calls methods on member variables. And the reason this is important is because now I can substitute these and I can make them behave however I want. I can make get host by name succeed. I can make it fail. I can make logger.error do nothing. Or I can make it pretend like it's full. I can model any sort of behavior I want in my test. And now let's show how we might actually, let's talk about what's changed here. So like I said, we've passed in the dependencies from above. And we've defined kind of the contract. What are the logic dependencies of this class? Well, I depend on internet host and logger. And that's the seams I expose to the outside world that can be substituted in a test environment. I'm avoiding any kind of free functions, static methods, global variables. Those are types of things that is not very convenient to substitute in D. I don't even think it's possible in D. There are languages where you can swizzle away and substitute global variables and static methods. D, as far as I know, is not one of them. Maybe you can do dynamic linker tricks. Try to avoid those. So let's talk about what a test might be for this. So I'm going to use a tool called dmocks. Has anybody here used a mock object framework before? So we have a couple. So if you haven't heard of them, so mock objects are basically a tool for creating an object that adheres to the conventions of and behaves exactly like any type of object you like, except its implementation is defined by you. You can tell it to do nothing. You can tell it to fail. You can tell it to have some sort of side effect or set a Boolean when it's called. You can program them any way you like. And it's basically a way of modeling the behavior of a system to control it. In this case, I'm using dmock to create a mock of the internet host class and a mock of the logger class. And mock frameworks generally have some way of recording and then replaying a series of events. So in this case, I'm going to say, hey, mock internet host. I'm going to say, we're going to call get host by name and pass in the host a.b.c. And that's what you're going to expect. When I say replay, it switches modes from recording what happens to actually getting ready to verify what's called. I'm passing in this mock object to the class under test. The class under test has no idea whether it's being passed the actual implementations or mocks that model the implementation. As long as they adhere to the interface of the class that is in its constructor, it'll work just fine. And then I call the method checkHost, and I pass in the host under question. And the last statement I'm telling it is all of the mock objects verify that they have behaved as I've programmed them to. Yes, Ali?
I don't see the connection of mocker to new host checker line.
I don't see the connection of mocker to new host checker line. So mocker here constructs for me a mock of the object internet host. Yes. So this is an internet host mock, and the variable logger is a mock of the logger class. Underneath the hood, it's actually making subclasses of these classes, but it just uses reflection to make no-op. I think, has anybody used like white hole or black hole in SD? They're all based on that technique for basically just stubbing out implementations of all the methods in a class. By the way, this is only made possible in D because of D's strong compile time reflection functionality. I'm going to spend a little time going into this in the end. But this is a lot of magic that in other classes has to be done either at runtime for Java or via complicated macros for C and C++. So D actually lets you do it at compile time in a fairly sensible way. This is a lot of information, so is everybody comfortable with what I've just kind of covered? Like this is like a pretty massive amount of information. So, any questions here? All right, one question?
When are the unit tests actually run? Which line of code is that?
When are the unit tests actually run? Are they being run by the mocker.verify?
Yeah, so the question is, when are the unit tests actually run? Yes, mocker.verify is the only thing that's going to assert in this case or throw exceptions. So this is a unit test that's just basically checking, does host checker actually call the methods with the correct parameters of the dependencies? And the mocker.verify is the actual assert. That's the actual test.
Okay.
This is actually not an amazing example of a unit test, because all this is taking the implementation of the function and turning it on its head and saying, does the implementation exactly match this test? Not a great test. I'm going to give another example of a more useful test.
Okay.
So let's talk about a more useful test. So a lot of times we need to test what happens in the success case. But just as important, and almost more important, is what happens in the failure case. And this is the thing that makes this technique really novel and useful to me, is just as easy as it is to simulate success, we can simulate failure. So let's go through a failure case. So just like before, I'm creating mocks for my internet host and logger objects. But now I'm going to program these in different ways. So I'm going to say, you're going to expect a call to get host by name with the argument ABC, and you're going to return false. And we're going to expect any number of calls to the logger.error function. And we don't care about the arguments that are passed. I don't care about verifying the log message. So basically, I'm going to expect that there's a call to get host by name. I'm going to program it to return false. And I want to make sure that we log an error. And now I can basically, when I do the same call to construct the host checker with the mock objects I've created, I can basically say, I want checkHost to throw. And then I want to verify that these series of operations happened exactly in that order. This is like right? If you think about it, because traditionally writing a test to verify that DNS fails, that sucks. Like that's really hard. Or as Andre likes to say, testing that close fails. Andre, have you actually ever written a test to actually verify what happens if close fails on a file handle? No, nobody has. Nobody does. Like, who writes a test to verify that close fails? Nobody does. But this makes it possible. You could actually model what happens. And guess what? My programs all crash when close fails. Like, in reality, like, I don't pay nearly as much attention as I should to what happens when close fails. Or maybe I wrote code that's supposed to enforce that close succeeds. Is all the code along the way exception safe, and does it correctly close the file handles that were open, the other file handles that were opened in the method? I can verify all of that now. This is kind of like a big jump. So is what I'm talking about here kind of clear? Does anybody have any questions about this? Is this kind of more in line with an actual test that is more interesting now?
Oh, yeah.
OK, cool. Now, again, this technique is appropriate for objects and interfaces and those kinds of things. There are ways to substitute functions by passing in function objects and other things. So I'm going to focus on objects, and because most of the testing literature you'll see out there comes from the Java world. And so most of the mocking frameworks and other things that you see are basically oriented around objects, but there's nothing magical about objects. Anything that can be substituted, that can be looked up dynamically, like a function pointer, or a function object, a class. A template could be a template function is another way you can substitute the behavior. These are all super, super valid, and depending on your circumstance, you may want to use one or the other. But as long as you can substitute the dependencies, you can make it testable. Because that is a common question I get from a lot of people when I see them run into this. Like, well, gee, making sure I have to have all these subclasses and wrap everything in an object, isn't that a lot of overhead? I worry a lot about function dispatch and vtable lookups. Totally right. And for whatever's appropriate for your circumstance, you need to make sure that you use the right trade-offs for performance and reliability and readability. In my experience, other than the lowest of the low-level code, an extra vtable lookup isn't going to kill you in application-level code, which is the majority of the tests that you need to run. Go ahead, Walter. I can repeat the question.
But couldn't you pass a lot of those parameters via template parameters?
Yeah, so the question is, couldn't I pass a lot of those parameters via template parameters? Absolutely, yeah. There's nothing that says
overhead.
Yes, exactly. There's no overhead if you pass them as, but there's a little bit of mental overhead, and there's a little bit of compile. If you get it wrong, the compiler tends to be a little bit more mysterious when you screw up at compile time. I'm going to talk about a couple more techniques that you can use to take more advantage of the runtime capabilities here. So I want to go over the good side of this technique, the bad side of this technique, and the awful side of this technique. So the good part is, when you write code this way and separate out the dependencies, the tests become trivial. Like, it's super easy to model. As long as you can create the models of the objects that interact with your code, it's really easy to test. The bad part is, this is an ugly, ugly constructor, and you might see this constructor in the field, and it has a whole bunch of arguments. And if I'm a client and I just want to create a host checker, why should I have to be bothered to create the internet host and the logger and all this stuff just because he happens to use it in his implementation? This is leaking implementation details to the outside world. Like, anybody who's experienced classes that leak their implementation details knows it's awful, and it ties you to that specific implementation of that class. So if that list of dependencies changes, you have to go out and find all the people that use you and update them as well. That's awful. So the dejected is that D is a modern programming language. So I bet there's a way to have it take care of these details so that we don't have to leak all of our dependencies to the outside world and wrap it up in a nice system. So what I'm going to introduce you is a system I've written called Deject. It's a dependency injection framework for D. So this is on GitHub, and I'm going to walk you through a bit of how it works. So Deject is a library that maintains a couple objects. So let me walk you through some of the core concepts. The top-level object in Deject is called the object graph. And to construct an object graph, you can give it one or more D modules. What it does then is it actually inspects at compile time all the classes in those modules and looks at their constructors to see if they're annotated with a special annotation. And what it does is it builds a graph of those objects and all those dependencies and creates all of the glue to wire them together at runtime. So even if I have my host checker object that depends on internet host and logger, I don't have to call the constructor that anymore. Deject inspects it and creates at compile time all the logic necessary to construct that object, construct its dependencies, construct the dependencies and their dependencies and so on, forming the full object graph and passing it in at runtime. The object graph contains a binding map, which is basically a dictionary that maps keys, which are names of classes, to values, which are objects that contain all the instructions for how do I construct this object and how do I construct the dependencies of this object. So there are basically 3 types of bindings that you might encounter. A binding for a class, like foo. A singleton binding. So one of the big things that you run into when you start relying on an external system to supply dependencies is, what is the lifetime of these dependencies? Who manages the scope of these objects? There are a lot of objects that, for stateful reasons, there should only be one of them in your process. Traditionally, you might write code individually to make that a singleton, but I mean, I'm sure people know singleton it's a bad word now, right?
Yes.
Okay. I'm going to tell you that it is still a bad word if you cannot substitute it in a test. If you can substitute it in a test this way, having a specified lifetime for an object is not a bad thing. And with deject, you can actually wrap your object and say, I'm going to define the lifetime for this object. If anybody asks for a bar, every time they ask for it, they happen to get the same one. They don't know that. In a test, I can substitute it, or if I need to change that lifetime later, it doesn't impact the code underneath. It just gets a different object. You can also create function bindings. Let's say you don't want to actually bind a class, but you want to bind just a free function and have it return instances of an object. You can do that as well. In this case, I might have a foo class that takes an A and a B as parameters. So the graph looks something like this. In the case of a singleton binding, he might wrap just another binding as well. So that's basically how the object graph is built. And the big part of this is that compile time, it builds like I said, the binding module contains this map that I described. Underneath, it's actually type infos, which thank you, D, for having native type info identifiers for classes. It's much nicer than a lot of languages. And basically, we're going to analyze the graph of dependencies at compile time to find all the dependencies. The very first time you ask for an object of type foo, it walks that graph, caches the dependencies, and stores it in this binding state object, which it holds on to. And it manages the object lifetime. So not just singletons, but there's other types of scopes you could imagine. So at Facebook, we actually use this system to handle, do any of you guys write products that the user can log into and log out of? There's a couple of you do. So a big problem that we have is, like, if we have a program that needs to handle a user logging in, doing 7 things, and then logging out, you need to make sure when you log out that the 47 things they did are cleaned up. And traditionally, you have this logout method that's 4,000 lines of code, and it reaches into this cache and that cache and clears them and deletes this file from disk, and oh, I forgot to delete that file, and that's a privacy violation. Dang, like that kind of thing happens a lot. You can manage object lifetime and define it to be whatever length you want. With singleton, it happens to be from process start to process finish, but you could have a login scope, which says from login to logout, this object exists, and after logout, it's released, and the garbage collector cleans it up, and you're guaranteed for it to go away. It's pretty cool. The compile time component of the system is what gets me the most excited, and this is the thing that I think is totally unlike any dependency injection system I've seen out there for C++ or Java or other things. Like, have folks used Juice, G-U-I-C-E, for Java? Got 1, 2 people. So you've heard a lot of these terms before if you've used Juice. It's a very common thing at Google for doing exactly this technique. But it's all completely at runtime. And especially on embedded systems, you just don't have the power to introspect at runtime all of your code and walk this graph of dependencies. So doing it at compile time is a massive win. So D's strong compile time introspection is what makes this possible. We can actually use standard modules to look at the traits of the classes to identify who wants to participate in this object graph, and then iterate through their members to identify all of the parameters and pass them in from what we've calculated in the object graph. So I've introduced a @inject attribute, stolen from Juice, of course, to identify the objects in your source code that actually want to participate in this object graph system. This is completely opt-in. Like, you need to design classes to use this construction injector technique. So the system only looks at classes that are especially annotated with @inject. And then we basically use the demixin technology to create, so everybody here, does everybody here know demixins? Most people do. So as a quick review, demixins are basically a type-safe, sanity-safe version of macros in C. They're every function and every method can be used, and every templated function can basically be used to mix in and generate at compile time segments of code that can be brought into other scopes. So they can be brought into class scope, they can be brought into function scope, where I believe function scope as well, right? Yeah, you can basically mix in some code at compile time anywhere. And that's what makes this performant and fast. So unlike other systems where you might have to look at this graph at runtime and do some RTTI to inspect a bunch of structs, this logic is all emitted at compile time. So basically, the only thing we have to do to actually make this code injected is add one line. So I'm going to import a module deject.attributes and add an @inject before my class. And that's it. Deject takes care of the rest to create the object graph and maintain it, and to create it at compile time and maintain it at runtime so that the caller can construct instances of these host checker on demand. And let me show you the turtles. This is turtles all the way down. So basically, you can imagine, once you actually go down this road, you can imagine that every single class in your entire system becomes injected. And to create a foo, you just ask the object graph, hey, object graph, give me a foo. Well, that might create a bar and a boz and 6 other objects, but you're completely isolated from it. So what ends up happening is that at whatever the top level that's appropriate for your code, whether it's main or some other object that doesn't participate in the object graph system, you need to construct an object graph and say, so I'm going to construct an object graph and pass in a module here. This is actually pretty unusual. You don't often see modules passed as parameters. But it is possible in D. I don't know why do you do have to use parentheses around the module name? Is there a precedence issue with the period? Sorry.
It's a precedence issue.
We should just leave the microphone there all day, I think. Yeah. So due to precedence issues, you do need to put parentheses around the name of a module if there's a dot in it. So I'm basically saying I want an object graph. Look at all of the classes in the module foo.hostChecker. In this case, it's going to have the one class I've shown here. Foo.hostChecker has one class hostChecker. And this is going to, at compile time, generate this object graph and stash away all the implementations. And at runtime, I'm going to say, hey, construct me a hostChecker. And that's it. I don't have to specify anything about loggers or other things. The idea is that logger and the other classes are either participate in this system, or I've manually written code that says, hey, object graph, if you ask for an instance of internet host, I'm just going to say, just call new internet host. So you can actually stitch in objects like library functions and other things that library classes and functions that don't participate in the object graph system. You can stitch them in to the object graph. And so I'm going to say, hey, create a host checker, and let's assume that there's more than at least one argument, and check the host. And that's the entire system. But now I can actually write all the tests for my host checker and execute the client code without too much fuss. I don't have to construct loggers, and if that list of dependencies changes, this code doesn't have to change ever, which is pretty cool. So, so my big hope here is that, again, this is pretty proof of concept at this point, right? Like this is just alpha software. But what would be really cool in my mind is if this kind of thing works and is proven to work, and we can make it work for templates, and we can make it work for function objects and everything else that's convenient in D, it would be really cool to say, hey, every code, just as the assumption that we have that libraries are well unit tested, we can now say it's trivial to make the assumption that every application is well unit tested because we have all these objects that can participate in the object graph, and you can substitute them out, model them in your tests, and treat them like treat them as simple dependencies. So that'd be pretty cool. So basically, to wrap all this up, pass from above and constructor injection are the ways to separate out the dependencies from your code. And this is the key to writing tests that don't bit rot, tests that fail only when the code underneath is actually changed and broken, and keeping your code healthy. You can use mocks like dmocks to control the behavior dependencies in tests. One note, the DMOX code hasn't really been maintained in many years. It is there out there on the internet. I don't remember if it's on GitHub or what, but I've modified it a bit to make it actually compile with modern DMD. I'd like to, we might need to fork DMOX since there isn't a maintainer currently, but if anybody's interested in maintaining it, come talk to me and we can work out some sort of system. And you can grab the source code for Deject today. It's on GitHub under Gertzfield deject. And that's basically it. So thank you very much, and I'd like to take the next 15 minutes or so to answer questions for you guys.
All right, so the question I asked earlier, how do you have different dependencies for your test run from your actual run? Okay, so that's a great question. So the main way with this, for a true unit test, the idea with constructor injection is you create a mock for that dependency. And the unit under test, it specifies in its constructor all the dependencies that you might want to substitute. So compilation dependencies for your unit test. Say you're depending on demock in your unit tests, but you don't want that on your dependency graph for runtime. I see what you're saying. So you're compiling your unit tests. There's nothing that says that your unit tests have to be in the same file as your implementation. I put them in, for some of my tests in deject, they're in a completely different directory. That's one way. Does anybody else know any other ways that you can actually make it conditional on? Can you scope you can scope imports, right? Yeah, so there you go. So yeah, you could import the scope. You could import demox inside the unit test block, and it would be just completely compiled out.
Will it still end up accessing the file if you don't ask to build unit tests?
The question is, will it still access the file when you don't build unit tests? I believe it's completely compiled out, right? The unit test block, even if it's syntactically incorrect, is it compiled without -unit test?
If you don't throw the -unit test, it has to syntactically compile, but not semantically, and no code is generated for it.
Does that mean including importing modules?
It imports the modules, but it doesn't actually go and import them. It just parses the syntax.
Okay, so they have to exist on the file system, but that's it.
No, they don't even have to exist. It just, the syntax has to be correct syntax.
Okay, so if I say import blah, 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 and it doesn't exist in the file system, as long as I don't compile with -unit test, it doesn't matter.
Actually, importing is a semantic operation, and if you don't specify -unit test, there's no semantic analysis done on the unit test block.
So there you go.
What's the impact on compilation times of doing this?
That's a great question. So the impact on compilation time obviously is not 0. I haven't done a benchmark yet on a large real-world system to see how this might impact it. I would assume it would be, I mean, there's so many methods in the standard library that are already done at compile time. I would expect that it wouldn't be a huge one, but mix-ins aren't free, right? The compiler does have to run on them. That's a good question. I'd like to benchmark it and find out.
Yeah, I'm mostly concerned about using traits, and if you create an object graph of everything that's in a module, yeah.
I would expect that such a thing would probably be fairly easy to optimize if it were slow. I mean, from what I have heard people complain about mix-in compile time performance before, but it seems like that would be a good project that would benefit everybody if we optimize the performance of that. Okay.
So I'm not a big fan of dependency injection, I guess, from bad experience with Juice, and one of the difficulties is it's hard to know ultimately what created an object, because it's a very remote thing. So have you thought about any kind of tools for deject that would give you that kind of information?
It's a great question. And so what he's talking about is you might get a backtrace one day that has this huge stack, and you see these 47 objects in them, and you have no idea where they come from. And ultimately, the responsibility for these dependencies does lie in the user. So basically, you don't see new foo in line in the code that's consuming foo anymore. The new foo is happening somewhere else, and it's kind of hard to mentally keep track of where it was constructed and why. I think such a system would be really cool to keep like a database of where did all the dependencies and the dependent on objects get constructed. That would be a cool project. What I found in practice is that's only really a problem if the constructors themselves do a significant amount of work. It's really when you're debugging logic inside constructors that becomes especially painful. And a good rule of thumb I found when working in this world is keep your constructors as dead simple as possible. And this is, from working in C++ and other languages, this is kind of a rule that you kind of see as a good rule of thumb in C++ as well. But keeping your constructors just limited to taking the dependencies and stashing them in member variables helps a lot. But it's not, this is not a panacea by any means, and I'm not saying that every class in every situation must participate in this system. This is a tool for writing code that can be reasoned about and tested about. It can be misused horribly, as I'm sure you've seen with Juice, like any other tool. So use it judiciously and make sure that you have, like you mentioned, the good logging and other frameworks in place to identify problems. If you're in a situation where it's really important to know exactly where and when objects are created and destroyed, garbage collection is another topic where it's like, I wish I had logging and control of where objects are created and when they're destroyed, but for the convenience of garbage collection, I've agreed to relinquish that level of control. And in the end, I think we all benefit from it. So my personal feeling on this is a really young area of computer science and computer engineering. We're going to see improvements. We're going to see standard ways of looking at logging for where objects come from. But I would be surprised if in 10, 15 years, we don't see people just expecting, like, why can't I write code this way? At Facebook, we use this technique in our Java code, PHP, Objective-C. We've started using it in C++ as well. And it's difficult at first because you lose that control, but once you get into that, just like with garbage collection, it's very difficult to imagine a world where you have to write tests that have all these implicit dependencies and become flaky over time and start failing randomly when the disk is full or when DNS decides to burp. So it's a trade-off, but I think it's worth it in the long run.
So you mentioned before that you could register existing libraries with the object graph. How and where would this happen?
So the idea is there's an object called a module, and a module is code that you actually write. The module is the code that contains all the mixins from the add-inject classes. You can also write your own modules and actually write declaratively, I have an object that provides this type. And this method provides type foo, and then you can construct it from the library however you wish. There are ways to wire up standalone functions to that. Those are the main ways to do that. In frameworks like Juice, you might see an @provides annotation that you can just stick on any method, and that will automatically create an entry to wire together an external dependency like that. I haven't written that yet. More questions? Well, I appreciate you guys taking the time to listen to this today. This talk was actually supposed to be half an hour, so I'm glad it went this long. You guys have a couple extra minutes to relax, go have some coffee, hit the restroom. Thank you very, very much for coming to the talk today and listening to unit testing in D. So go make your code testable.